Hello, it's Keith here, and this is lesson 2 of my PDP-11 assembly programming tutorials. Now, we've been looking at the basics of the PDP-11 last time, and this time we're going to be looking at the addressing modes. I think these are quite interesting because they, in a lot of ways, resemble the 68000 processor, and I believe that the 68000 was in some ways based on the sort of ideas of the PDP-11, so that's possibly not particularly surprising. And as I said before, this is where I really think that the PDP-11 comes quite fascinating as a sort of historical artifact, because we do see where a lot of the later ideas sort of got their genesis from. Anyway, we're going to be looking at it today. We're going to go through each of the addressing modes, and we're going to try them all out. Now, you can see on my website, as always, there's some documentation, and each addressing mode will have a numerical representation. So this is 0R, and R would be the register number, and you can see going down we've got all of these, and we even go to sort of 27 and 77 here. And you may wonder what those are. Now, we're not going to really cover that today. What they are is, this is the octal representation of that addressing mode within the bytecode of the compiled commands. Now, if we're using an assembler, we probably don't need to worry about that. But I thought it was a good way of separating out and ordering the addressing modes. So they're just there, but as I say, you don't need to worry about them because we're going to be using an assembler. Anyway, let's go over to today's code and let's see it in action. Okay, so the first mode we're going to be looking at today is register addressing. So let's have a look at that. You can see it just here. Now, this is the absolute most basic, really. We did see it last time. This is where we are using the values held in registers. Here's our emulator just starting up here. A bit small, I apologize for that, but you can see here that we've loaded a fixed value, an immediate value, so to speak, into R1 here, and then we've moved from R1 into R0 here, and you can see that here. R1 here contained 1 and a load of 7s, and then after we did the move, R0 also contained the same values, so we've moved the value from R1 to R0 here, and that's what a register addressing is. It's where the value in a register is being used as the value in the source or the destination. Very basic, that's the simplest one, and we needed to get it out of the way, of course. Now, we will look at the immediate addressing, which is sort of this thing, later on, but in the order we're going to be looking at today, it doesn't come up just yet. Okay, so next we're going to have a look at registered deferred, as it's called by this processor. Now, this would be called indirect addressing on some systems. This is where the value is taken from the address in a register. So if our register contains 1000, it's not the value 1000 that's being used, it's the value at address 1000. And the way we represent this on this assembler is we have our register and we just put it in brackets, and that will tell the assembler to compile a command that will use the address in R1 as the source of the data here, and we will be storing in R0 here. Now, of course, we need some test data, and you can see it's somewhere around here. Here we go, we've got some test data here. Okay, so let's just fire this one up. And let's just lock that to the top of the screen so we can have a look at it. Okay, so what have we done here? Well, what we've done is we've loaded in a value into R1, 1616 in this case, and we've loaded the value from that address into R0 here. Then we've added 2, moving along 2 bytes, and we've loaded in from that address, and then we've added 1 and we've loaded in from that address as well. Now let's just scroll down here and have a look at the source data that we've read in from. Okay, so test data here is the data we've read in from, and that must have address 1616 here, and then we've loaded in from that address a word, which of course is this 111 here, so you can see we've loaded that in twice here. Then what we've done is we've added 2, so that has gone up from 1616 to 1620. Why has it gone up to 20? Well, this is an octal address. Remember, this is from 0 to 7, so when we get up to what would be 8, we actually rolled up to 20 here. So then we loaded in the next word, which was 222 here, and you can see that just here. Okay, now what we did next, if you remember, is we actually increased by 1 byte. You can see this has gone up from 1620 to 1621, and then we loaded in another word. Now you can see that just here, and we loaded in the word just here. Now what we effectively did is attempt to read in from an odd boundary memory address, and the PDP-11 doesn't like this. It's a 16-bit processor and it works on even boundaries. So when we tried to load in we actually got the exact same value a second time because we're trying to read the word from the odd boundary and we can only read from an even boundary. So that little test there was just to show, you know, you can't do that kind of thing with words. You could do it with bytes, but you can't do it with words here. Okay, so that's how we can read in from an address in a register. Now, the next one we're going to look at is auto increment. Now, in the same way as last time, we can use the address in a register here. Now, again, this time we're going to load the address into R1 here, and we're going to load a word in from R1, the address in R1 into R0 here. But this time, rather than doing an add to here, we're going to get the processor to do it for us. You can see we've put a plus at the end here, which means after reading from the address in R1, that's what the R1 in brackets means there, increment the address because of this plus. And because we're reading in a word, we're going to increment by 2. And you can see that has happened just here. You can see here we've gone from 1620 to 1622 here. And so we've read in from a word here, and then we've read in a word here. Now, alternatively, we can read in a byte. We've done that just here and here. But when we do that and we do our increment, we can see we're going up just 1 byte each time. And of course, this time, in this case, we were reading from an odd boundary. But as long as we're reading bytes, not words, that will work just fine. So you can see there we're able to read in our test values just fine. Now, there is a rather strange version of this that sort of surprised me a little bit. Now, this is known as auto increment deferred. Now, in the case here, we were reading from the address in a register and incrementing that address, but we can actually sort of add another layer of abstraction, so to speak, and have a list of addresses point to that list of addresses and automatically increment reading that list of addresses. Now for clarity, let's just see what data we're going to be working with in this example here. Okay, so you can see here we've got a set of pointers. So the first pointer points to test data, the second pointer points to test D2, the third pointer points to test data again, and the fourth pointer points to test D2 here. Now what we've done is we've loaded in the pointer to that list here into R1, and then by specifying the at the start, we are specifying that we want to read from the address at the address in R1. A little bit confusing, but that's what we've done here. So you can see here we're actually loading in the address 1634 here, and there's a dump of the memory at 1634 here, and you can see it's alternating between 2 pointers here. And so when we read in, incrementing, we are first reading in from the address at the address in R1, which is this address here, and we get the value 111 here. Then we increment R1 and we do the same. So this time we'll be loading from this address here, which returns the value 777. We then increment R1 again. This time we'll be loading from this address here, and that gives us the 111 again. You can see it just here. Now that time we were loading in just a byte here, and then finally we load in a byte again from the address, again incrementing R1, and this time you can see we've got effectively 377, but it's been extended to fill the full word. It's become 1 5/7 there. Now, as I say, this is one that's a little bit confusing maybe, but basically, as I say, if we put the at the start, we're using the address at the address in R1, because again, we've got the brackets here, and it's R1 being incremented here. The data at this address is unaffected by these commands. You can see that's the case, because none of this data has changed here when we've done that little memory dump there. Okay, so that's how we can use that addressing mode. Let's move on to the next one. Now, we've done auto increment there, but of course there is a matching auto decrement. Let's have a look at it. It's pretty much what you would expect if you're familiar with 68,000. Effectively, all we've done is we've put the minus before the address in brackets, and that will reduce the register before the value in the register is used as a source address. So I think that's exactly the same as 68,000. So we're going to just load in a byte twice here from the address, and then we're going to load in 2 words, and our data is actually the end of this source data just here. So we're going to be using the same data, we're just going to start at the opposite side, and that's why we're reading in the bytes first this time rather than the words. Okay, so let's fire that up. Okay, so you can see here we've loaded in a 777 here, and then we've loaded in a 666, and then we've loaded in 2233, and finally 222 here. If I just lock this to the top here, and if we have a look at that end data here, you can see the end data is here, and the 7.7 that we loaded in first is there. Then here's the 6.6. Now, when it came to reading in the word here, we are now on an odd byte boundary here, and so this has caused our code to read in the values sort of incorrectly. So when we've read in here, we've actually ended up with the value 2233 here, and that's because we've sort of half read in a byte. Now, the final value, although we're still on an odd boundary, we're now pointing directly at this word, so we've successfully read in this value here as 222 here. And if we read in another value, we would get the 111. If I just add in another command here and run it again. We have loaded in the 111 just there. So that's how we can do a auto decrement. The auto decrement always happens before the read, you can't do it afterwards. Increment always happens afterwards, decrement always happens before on this processor. Now, in the same way as the auto increment deferred, we can do an auto decrement deferred. Again, we're now using the address at the address in a register here. So we're going to be using the register R1 here, and again we just put the @ symbol at the start and the minus after the @ symbol but before the brackets there. If I just lock this to the top, and if we just have a look at this data here, so we're reading in the same data as before here. This time though we're starting at the end of the list of pointers here, and again these pointers point to either this test data here, so we're reading in 1s, or they point to this data here in which we're reading in 7s. Now here we read in a byte, and so that was byte extended to fill the word. That's why it's become 1 and a load of 7s here. That's because that value has been extended. Now here we're just loading in the 111 here. You can see that that's from just there. And then here when we're reading in a full word, you can see there's no byte extension. But basically we're reading backwards through this list of pointers here, and that's where this data is coming from. And as I say, that's just because we've got that at the start of the command, and then we've got the minus telling it to auto decrement, and then the register in brackets, which is saying the address in that register is the source. Of course, all of these can be done as a destination as well. I'm just using the source here because it's easy to demonstrate. But so these commands can be as a source or a destination on the PDP-11 processor. Okay. Now, like the 68,000 and many of the other processors that followed it, we can use indexes. This is again another of the things I think the PDP-11 was pretty much maybe one of the first on that sort of became very popular in other processors. So in this case, we're going to use the address in a register, and of course the register value can change at any point, but we're also going to use a fixed offset. So here we're using the address in R1 and +2. Now the way this will work is the address in R1 will have 2 added to it, and then that resulting value will be the source address. Okay, let's fire this up and we'll see that working. So we've loaded in from various offsets here, 2, 4 and 5 here, and we've loaded in from the data address test data which we loaded into R1. So first we loaded in from the base address test data, so you can see we got 111 here, and then we loaded in from offset 2, and that gave us 222, and then we loaded in from 4 and 5, and that gave us 3 and 4. Now if we look at our test data, that's offset 0 here, that's offset 2, and then offset 4, because this is 2 bytes, will be this value here, so you can see that's been loaded in, and offset 5 will be this 1 byte here, and you can see that's been loaded into just there. Now in this case we've used a numeric value here, but we can define a symbol to make things easier for us if we want. For example, if we were using different memory at address R1 for different purposes, like an XY position of a game character or something, we can create a symbol. So if we created a symbol called XPOS here, and we defined that as 2 and YPOS equals 4 maybe, and then we can just specify these labels instead, these symbols, as part of our command here. And if we just compile that again, it will run just the same. And yeah, this is handy if R1 is some kind of data structure and we want to be able to remember what the function of each element in that data structure is, for example, in an X and Y position, and you can see the code will work just the same. So that's something that's definitely worth bearing in mind. As I say, this is something that is very standard in the modern processors, didn't really exist in things like the Z80, and it's very interesting to see it on such an early processor in the PDP-11, and so very impressive to see that. Now, index deferred, this again is a combination of the two. So we're using the address in R1, and R1 is going to be a list of pointers, and we are going to add 2 to that address, and we're specifying the at the start here, then we're specifying the offset, and we're specifying the address in R1 here. Okay, so let's fire this up again. Okay, so we've got our test data again. So we've got pointers to the values 111 and 777 here, as we had before, and we're loading the base address into R1 here, this test address. So we're reading in from the pointer at the address in R1 here, which is this first one just here, and that will return 111 here when we read in a word. Next, we're using that address in R1, but we're going to add 2 to it. But notice that the address in R1 doesn't change because it's an index, not any kind of increment. And so we're then reading in from the address in R1 with +2, which will point to here, and that value is the 777. We're then doing the same with bytes. We're adding 4 this time, again not changing R1, so this time we're going to be reading in from this address here, which is again the same as the first address, so we get the 111 again. Then we're reading in a byte from the address +6, which is this last one over here, and so again we're getting the 777, and because we're loading in just a byte, we're getting 3 777, and that's being sign extended to fill the word, so that's why we're getting that value here. Now, I'd say these are probably a little bit confusing. I have not done really a whole lot of PDP-11 programming, just a few little basic things, and these deferred modes are something that isn't really something I've come across needing, but they are very powerful. It's certainly nice to have so many options available to us, but don't worry about it if you're a bit confused by them. But as I say, basically that's what it means when you have the at the start. Now, we've gone through a lot of quite confusing modes there, to be honest, and we've actually sort of skipped over some of the stuff that would be more basic in most cases. Now, there's a good reason for that. Now, if we just go back to our documentation, now here's the documentation on my website, and I said before that there's these numbers at the side of each one, and index deferred that we just looked at is 7, mode 7 with the register. Now, if we use the program counter as the parameter register, now these previously discussed addressing modes suddenly become a new addressing mode, so to speak, and we don't have to worry about how this works. It's actually the assembler that does it for us. But if we use register 7, the program counter, with addressing mode 2, which is auto increment, well, this will actually effectively become an immediate value reading in. And if we use addressing mode 3, which is auto increment deferred, with the program counter, this will effectively become an absolute read of a fixed address. And the reason for this is that the address that we're reading from, or the immediate value we're reading from, is actually the following word to the current running command, and it's the program counter pointing to the current running command. As I say, I know that's weird and confusing. Don't worry about it. It's just it kind of made more sense to me when I sort of saw that, and that's why we're doing them in this order, and that's why, as I say, they have these weird numeric values, each addressing mode does. So we'll carry on now, and we'll have a look at, actually, ironically, those simpler ones that are based around the program counter. Now, immediate addressing, this is really the most basic, and I say it's slightly a shame that we're covering it so late, but this is a program counter one. So we're loading the fixed value into R0, and we specify that with a hash here. So here we're loading 1, 2, 3, 4 into R0. Here we're loading 2, 3, 4, 5 into R1. And these, of course, are in octal because we didn't specify otherwise. And if we just run this test, you can see 1, 2, 3, 4 in R0, 2, 3, 4, 5 into R1. Very simple there, immediate values. And the assembler, as I say, will directly compile those values into the following word after the assembly command itself. And that's why it's effectively a program counter based addressing mode. Next, we're going to use an absolute address. This is where we're reading in from a fixed address that never changes. If we have a look at that. Okay, so here we've got our @ symbol to tell it to load from an address, and we're using a fixed address, so we've got our hash symbol here, and we're going to load from test data +2 into our 0, and then we're going to load from octal address 1000 here into our 1, and who knows what's going to be there? Well, we'll see because we're doing a little memory dump. Okay, so we've loaded in from test data +2, and we've loaded in 222. That's test data there, and you can see the offset 2 bytes. The second word is 222 here. Then we've loaded in from hexadecimal 1000 into R1, and we got 12700 here, and you can see if at this dump of 1000, 12700 here. So if we want to load from an absolute fixed address, we use an @ symbol, then the hash, and then either the numeric address or a label that will, or a symbol that will define that address here, and that's what we've done there. Now, there's another 2 we're going to discuss. They're quite complicated, and I don't think you're going to need them, but for completeness, we're going to do them. Now, these are relative to the program counter. The program counter, rather confusingly in this assembler, is denoted by the dot symbol here. So what we've got here is we're loading from the program counter plus decimal 16 bytes. So we're loading from 16 bytes after this command, and then here we're going to load from 12 bytes after that command. Well, let's fire this up and let's see what happens. Okay, so we've loaded in 114422 here, and you can see that just here. Now, why is this command got 16 bytes added and this command got 12 bytes added? That's obviously that's a 2-word command, so so we're having to add 4 bytes for that, 4 bytes for that. This is also a 4-byte command. The call is 2 bytes and the address here is 2 bytes, and this is a 4-byte command, and the jump is 2 bytes and the infinite loop label is 2 bytes. So 4, 8, 12, and that's why we're adding 16 here and adding 12 there. Now, as I say, I don't think there's any real case you'd want to necessarily do this in your average code, but it's an addressing mode that is covered in the documentation for this system, and I try and do a complete tutorial, so we've got it here. Okay, now fortunately we've just got one last one. Again, I don't think you particularly need it, but we're going to cover it for completeness. Okay, so this is a relative deferred reading. So we're loading in again from the address at the program counter plus an offset. So whereas here we were loading in a fixed value, now we're loading in from an address label specified in a relative location to the program counter. So in the same way as before, we are adding 16 bytes here to point to this data here, like before when we pointed to this data here, and then 12 bytes. But this time the data isn't a fixed value, it's a pointer to a label effectively with some test data in it. So if we just compile this, we are going to load in, and we've got 777 in both cases. Now, as before, we've got the dot, which is the program counter, plus the decimal offset. If I didn't have this part, we'd be specifying octal. If I put in X here, and I put in 10 here, it would work the same, because that's hexadecimal. See, so that's worked just fine. So, you know, these are entirely optional. And we could, of course, use octal, but I thought it was clearer in decimal. Now, if we took away the @ of course, we'd now have the exact same command here. So rather than loading in from the address at this position, we'd now be loading in the data at this position, which would be the label address of test D2 here. If we just run that, and we've got the address 1636, which I guess is that label position. I can't remember. Okay, so there we go. I think that's actually all of the addressing modes on the PDP-11. Some of them are a little bit tricky, but as I say, a lot of them you're not really going to need for basic programming. The deferred ones you can probably avoid in a lot of cases, but as I really find it fascinating just how powerful this old processor from the 70s really was compared to say things like the Z80, and even, you know, when you compare it to processors like the ARM and things and the modern x86s and things, yeah, there's a lot of stuff that it's quite impressive to see how far back these sort of have their heritage, and to see just how powerful this early processor was. We're going to be carrying on, of course. We're going to be doing some probably ironically easier stuff next time. We've kind of gone over some quite technical things this time, but I hope you've enjoyed it. I hope you found it interesting. If you do, please like and subscribe, because that helps with the YouTube analytics, and anyone else looking for this kind of thing will sort of hopefully find it. You can get all of the source code for today's example on my website, and the build scripts and things, so hopefully you can run these examples yourselves and have a bit of fun. I hope you'll join me next time. We're going to be looking at other things. We're going to be going into the stack and lots more mathematics commands, and we'll be doing some graphics on the UKNC at some point in the future. Hope you enjoy it. Thanks for watching today, and goodbye.